Okay, so now we'll start by I'll do a few examples. Firstly, I want to do this one here, which is a semicircle. Yep. And I'm going to rotate that semicircle. I'm going to rotate this guy around the x-axis, but only from 0 to, let's call that 6. Okay. So that's going to spin around like that. Sorry. That's going to spin around like that. And I'm going to end up with a hemisphere. Okay, now sorry for my bad drawing, but hopefully you can see the hemisphere there. Okay. Now we can check our answer because we know how to do a volume of a sphere. So let's just check it's right by saying, well, the volume of a hemisphere is a half of 4/3 by pi by the radius squared, and the radius in this case is 6, which is 6 squared, which is 4 over 6 by pi r cubed, sorry. There we go. That's a 3 up there. By 216. Yeah. And that is, what do we got there? 6 into 16, that's 36 by 4, which is 36 by 4 is 144 pi. Right, and that's in units cubed. So that's what our answer should be. Now we're going to do it using calculus. I know from before that the volume of a solid equals pi times the integral from, we're going from 0 to 6, yeah? From 0 to 6. And we're going to do f of x, the formula for, or the equation I should say, for a semicircle is this. And then we have to square that and dx. So let's see what happens. Well, we get pi. That's squared. We'll get rid of the square root. So I've got 36 minus x squared dx. Integrating, I've got 36x minus x cubed on 3. And that's from 6 to 0 equals pi times 36 by 6 is 216. 216 minus 216 divided by 3, which is 72. And then the minus, the zeros will just, they're just zeros because there's an x term in everything. Minus 0, 216 minus 72 equals 144 pi units cubed, which is the same as this. So great, that works. What I'd like you to do now, just for an exercise, I want to find, I know that the volume of a sphere is 4/3 pi r cubed, okay? Let's take that one there from minus r to r, okay? And the equation of that, I'm going to spin that around. Whoop, whoop. So I'm going to end up with a sphere. It's the worst sphere I've ever drawn, but that's okay. So we go volume equals pi times the integral r to negative r square root of r squared minus x squared dx. Now, just give that a go. Okay, you know what the answer will be. It'll be 4/3 pi r cubed. And it should bring you immense satisfaction when you get that answer out. For the next example, we're going to rotate this line or spin this around the x-axis from x equals 1 to x equals 2. Now this is our y equals 3x minus 2. 1 to 2 is going to be, well, let's say from there to there. Okay. I'm going to take that guy there and spin him around the x-axis. So what's that going to look like? You could use GeoGebra, that link, to have a look, but I'll just attempt it here. So you can see that we're going to get this kind of, well, it's like a cone, with a truncated cone, is that what you call it? Cone with the top chopped off. So you can figure that out using the formula for a cone, but you can do that if you want to check. We'll just do the calculus here. I'm spinning it around the x-axis, so my formula equals the integral from 1 to 2. I take the x values. Okay, I take these x values, that's 1 and that's 2, of y squared dx, and don't forget the pi. Now what is y squared? Well, y is 3x minus 2, so that equals pi times the integral 2 to 1 of 3x minus 2 all squared dx, which equals pi. Let's integrate. Donna, we can expand that, or we can do powers. Let's expand it just for laughs. 2, 1, 9x squared minus 12x plus 4 equals, now we can integrate pi integral 9x cubed on 3 is 3x cubed minus 12x squared on 2 is 6x squared plus 4x. And obviously that is now bounded, and I'm going to put a 2 and a 1 in there. Subbing in, equal pi, subbing in the 2, I get 8, 24 minus 24. Okay, 24 minus 24, so don't worry, it'll work. Plus 8 minus the 1, which is 3 minus 6 plus 4 equals pi. What have I got? 8 minus, well, that's a 7 minus 6, that's a minus 1. So I get 7 pi units cubed. For the next one, we're going to rotate around the y-axis. So spin it around that way. We're going to go y equals x squared plus 1. I've put there. We're going to go from y equals 1 to y equals 5. Okay, so we're going to go from here, y equals 1, to here. I'm going to take that area there, and I'm going to spin it around to get my cup, my cup that falls over. All right, so we've got that solid there. Okay, now I'm spinning it around the y-axis, so I know that my volume equals pi times integral from 1 to 5 of x squared dy. Now remember, I'm spinning it around the y-axis, so there's a dy there. Okay, x squared. Well, if I look over here, y equals x plus 1. So what's x squared? This one you don't have to square it. Like up in the top one, we actually squared that function. But here, x squared is already kind of given to us. If y equals x squared plus 1, that means x squared equals y minus 1. So that'll become pi times the integral 5, 1, y minus 1 dy. So look for that little substitution thing, just the rearrangement that you can then chuck in. I can then integrate this guy, what's that, y squared on 2 minus y from 5 to 1 equals pi 25 on 2 minus 5 minus a half minus 1. Now what does that come out? That's 12 and a half. Oh, sorry, bit of a lag there. Let's bring that down. And then we've got, so that's 12 and a half. 12 and a half minus 5 is 7 and a half. Let's go 7.5 minus a half minus 1 is minus a half. And then that's plus a half, which is 8 pi units cubed. So that's the volume of this cup. That's exactly the volume 8 pi, which is 24 and a bit. That's great. Alright, for the next example, I want to do sine x. Whoa, sine x. Okay, and I want to, remember we saw it before, I want to spin this guy around, just one of those balls. Okay, one of those guys there. To have a better look at what it looks like, so there we can see we've got sine x, and I just want to find that first, look at that lovely shape. I wonder what the volume of that is. Okay, so I just want to find one of those. To do that, I'm going to integrate. Well, I'm going to spin it around dx axis. There's going to be a dx on the end. This is y equals sine x. So I'm going to go volume equals pi times the integral. Where am I going from here? I'm going from 0 to, where does that cut? Pi. 0 to pi of y squared sine x squared. And it's about the x-axis, so it's dx. That can just be written as the square of sine pi to 0 of sine squared x dx. Now how do I integrate sine squared x? This was done in a previous video, but I'm just coming back to it to remind us. Pi integral of pi and 6, that sine squared x, by rearranging using the cos double angle, that'll come out at a half minus a half cos 2x dx, okay? Now you might want to look that up. This will then integrate to, sorry, pi, there we go, we got that there, and we got x on 2, cos minus cos goes to minus sine, so we get minus a quarter sine 2x, and that's going from pi to 0. That 0 is just going to be nothing, because sine of 0 is 0, and 0 on 2 is 0, so we're only going to get that first term, and that pi on 2 minus a quarter sine pi on 2 times 2 is pi, and then I get my minus 0 there. I'll just chuck that in. Okay, and then that is sine of pi. I know sine of pi is 0 because there it cuts right there. So I get pi squared on 2. Pi squared on 2 units cubed. That's pretty neat. Pi squared on 2, exactly. That lovely little shape. All right, one more example, and we're going to do the volume between two curves. Alright, so volume between two curves, or volume of an area between two curves. This is a nice easy example, okay, but the procedure is the same for all of them. So I thought we'd just do something nice. What I'm going to do is take that area and spin it around the x-axis. Okay, it's going to be a little hard to see, but what is going to happen, you're going to get this weird little thing here. Okay, I'll put up something from GeoGebra so we can look at it a bit nicer. So here I've got my line y equals x. There's y equals x squared. I want to take that yellow bit and rotate it around the x-axis. Now just watch what it looks like. Oh, bah. So it's a little better than my drawing, but hopefully you can see what it is. It's a cone with a straight outside and a curved inside. Yeah? Alright. How are we going to do that? Well, what we're going to do is we take that. That's the cone. Yes? That's when the blue line is rotated around the x-axis. That's when the red line is rotated around the x-axis. Our bit, our yellow bit, is the blue bit minus the yellow bit. Cool? Alright. So it's that cone with the curved inside. So we can draw that out here. We can say, well, my volume is going to be equal to the big cone. Yep. And I'm going to take out the weird, this thing. Alright. Now what I'm going to do, I'm going to call this one the volume made by the top curve. This one here. And this one over here, I'm going to say that's the volume made by the bottom one. So, volume equals, the volume made by the top one, or that blue, dark blue line, is pi times the integral from, let's say, a to b of y top squared dx. Okay with that? That bottom line is going to be minus pi times integral of b to a of y bottom squared dx. Alright, now that's kind of the formula, but we're going to simplify it a bit, and we're just going to factorize out that pi and the dx, and I can do that with my integrals. It's pi times integral of b to a y top squared minus y bottom squared dx. And that's it. And that's similar to the area between two curves. Remember when we did area between two curves? It was y top minus y bottom, but here I've got them squared. Now note, big just thing to note, that is not equal to y top minus y bottom squared. You can't just minus the functions like we did for area and then square it. And why is that not equal to that? Well, if I expand that out, I've got that extra term, don't I? I've got the 2 y top, y bottom. So you have to square them and then subtract them. Okie dokie. Back to our example. We can actually do it now. What the first thing that I didn't do, I just left that out for now, but one, you have to do, find points of intersection. Find points of intersection. Now, in this example, it's fairly easy, okay? I did that just so we can rush through this example. It might be trickier on other ones, and you might have to do a nice careful sketch to see what happens. But let's find those points of intersection. Well, the top curve, when x squared, when the bottom curve equals the top curve, when x squared equals x, don't just cancel your x's. I'm watching. x squared minus x equals 0. Factorize out x minus 1 equals 0. X equals 0. X equals 1. Now, you really could have done that by inspection. I know over here that is 0 and that is 1. Or 1, 1 actually, isn't it? But again, 0, 0, 1, 1. Pretty easy on that example, and it'll probably get harder. But chucking those values in here, then I get volume equals pi times the integral from 1 to 0. That's those values that I just found. From 1 to 0. Of top curve, which is y equals x squared minus the bottom curve, which is y equals x squared dx. Again, pretty straightforward integration here. Equals pi. I'll do another line. Integral 1, 0, x squared minus x4 dx pi x cubed on 3 minus x5 on 5 from 1 to 0, which equals pi. That's 0. See, you know, that 0 term's going to, which saves us a bit of time. The second term's going to be 0. Pi, a third, minus a fifth. And then I do my fractions here. This is why we did fractions all that time ago. 15. What's that? Pi on 15 units cubed. Okay, so that's it. Volume between solids. Find the point of intersection, okay? Stress that. You've got to see which bits are done. Then this guy here, you can just remember that. Top squared minus bottom squared. Okie dokie. Thank you very much.